Yeah, so welcome back. So before I begin the next second lecture, so there was one name that I forgot to mention over here, so I would like to mention that. So it's Imanubilov. And several others as well, but this was a name that I wanted to mention. Okay, all right. So now let's come to lecture 2. Sorry. Okay, so so recall that in the last lecture, the first lecture, what we did is we showed that the linearized the linearized Calderon problem is injective near constant conductivities. So we actually did this for gamma is equal to 1, but you can actually do this for any gamma. The result, any gamma constant, then the result is going to be the same. Okay, so now what I want to do is, so in this we actually want to focus on the nonlinear. Okay, and so this is the theorem that I want to do. So this is due to Sylvester and Ullmann. I think it's 1989. Okay, and so the theorem is as follows. So let omega contained in Rn be a bounded. You can think of this with nice boundary and things like that. With smooth boundary. And n bigger than or equal to 3. So let gamma 1 and gamma 2 be two positive C2 functions in omega such that lambda gamma 1 equal to lambda gamma 2. Okay, so then gamma 1 equal to gamma 2 in omega. And so what is lambda gamma 1? So lambda gamma 1 is the map that takes F to d gamma du gamma du d nu, right? So that is that's a map. Or you can also think of this in terms of the weak formulation. So it's going to be integral gamma grad u grad v, and so where u is such that u has the boundary value f and v is in h10 of omega. So this is what we did when we considered the power. So you can do both of this from one to the other by integration by parts. Okay, so when gamma 1 is equal to gamma 2 in omega. So so the fact that this is C2 functions, this is actually going to play a role. So that's one thing. And the other thing is that the initial approach of Calderon is also going to play a role in this proof. So let's actually go through the steps of the proof, the main ideas. Okay. So the first step is to actually not consider the following problem. So not consider this. So we don't want to consider this equation. We actually want to consider a perturbation of the Laplacian. Okay. So we actually do a transformation. So we do a transformation to obtain a Schrodinger equation. Okay. So so what is it that we do? So what we do is the following. So we actually consider So we actually transform. So we transform to something of this form. So minus Laplace plus Q V equal to 0. Okay. And V on the boundary equal to F. Okay, so the way that one does this, it's quite straightforward. All that we need to do is the following. So we actually look at so this is a very easy transformation. So you just look at V is equal to U by root gamma, something like this. And so just substitute. Sorry, actually it should be the other way around. It should be some power of gamma. So U equal to V by root gamma, something like this. Okay, just substitute this back into this. So here is where I use the fact that gamma is bounded below by a positive constant as well. And just go through the set of calculations, and then you will get the following equation, where this Q here is actually so note that Q is equal to Laplacian of root gamma by root gamma. Okay, so that's one thing. So once you do, so this is just a routine calculation. So let me not do this. So just 1 second. I think I got this right. If the power is not correct, then there will be a problem. Just 1 second. U by root gamma. Yeah, I think this is not right. So this is it's either yeah. So you take, okay, I think this is fine. So U is equal to V by root gamma. Yes, this is correct. Because now when you substitute this U is equal to V by root gamma into this, right? And just go through the calculations, then you will actually get this. You will actually get this with this. Okay. And so therefore, now what we have done is we have transformed the conductivity equation to a perturbation of the Laplacian. And I'll actually explain in just a second as to why this is important. But what we also want to do is we want to relate. So now so what is the information that, so this is the first step, right? So now the second step is to relate the DN map, the Dirichlet-to-Neumann map of the conductivity equation and that of the Schrodinger equation. And that of the Schrodinger equation. Because so what is the question that is given to us? The question that is given to us is, or the information that is given to us is information about this, the Dirichlet-to-Neumann map corresponding to the conductivity equation. But what I want to do is I want to relate that to the conductivity, to the Dirichlet-to-Neumann map of the Schrodinger equation. Now the Schrodinger equation is minus Laplace plus Q, where Q is of a special form. Now, notice, so one thing that I want to emphasize is that if gamma is the original conductivity gamma is null infinity and it bounded below by a positive constant, then that is well posed, right? But in general, this minus Laplace plus, let's say, QV, that's not well posed, right? For instance, you take Q to be Dirichlet eigenvalue, right? So it's not going to be well posed. But I'm not going to show this, but one can actually show, it's not very hard to show that for Q, which are conductivities of this form, then this is a well-posed problem. Or in other words, minus Laplace plus QV with V on the boundary being an F, which is in H half, that's going to have a unique solution. Okay, so so for conductivities which are which for potentials Q, so Q are what are called as potentials arising from of this form, which is Laplace root gamma by root gamma. Then this minus Laplace plus QV with V on the boundary being a Dirichlet has a unique solution. Okay, so so therefore what we do is, instead of looking at the conductivity equation, you look at this minus Laplace plus QV, that equation. And so far, in dimensions 3 and higher, pretty much all the approaches have been based on perturbations of the Laplacian. And there are some cases where, for instance, in the case of manifolds, you do not have the Laplacian, or you have the Laplace-Beltrami operator. But even in the case of the Laplace-Beltrami operator, there is one direction which is Euclidean, and that seems to be quite crucial for the construction or in solving such a problem. And at least this is to the best of my knowledge, that almost all the approaches have been based on construction of solutions modeling on the initial approach of Calderon in 3-dimensional scenario. And for that, the fact that you have to have a Laplacian, or you have to have a Laplace, or you have to have a Euclidean direction seems to be quite crucial. Okay, all right. So this is one thing, and so then what we have is the following. Right. Yes. So let me just state this as a lemma. Again, I'm not going to prove this. This is a computation. So lemma. So gamma, let's say, belongs to C2 of, let's say, omega closure, and Q is Laplace root gamma by root gamma. Okay, so then, so lambda QF, where lambda QF is actually D, in my notation, it's going to be dV d nu. Okay, but you see that I do not have this information, right? So what I have is the information about the Dirichlet-to-Neumann map corresponding to the conductivity equations. I want to relate the Dirichlet-to-Neumann map corresponding to the Schrodinger equation with that of the conductivity equation. So this relation is given as follows. So this is equal to gamma to the minus half of lambda gamma of gamma to the... Sorry, any questions? I can't hear you. I'm not able to hear you. Okay, let me continue. If there is a question, you can ask me later. There seems to be some disturbance. Is it from my end?
No, I think it's Pradeep's microphone. Pradeep Kumar.
Can you please mute your microphone, Pradeep? Thank you. Okay. All right. So, yeah, so lambda QF, so that's going to be equal to, so lambda gamma of gamma to the minus half F plus half gamma to the minus half d gamma d nu of F restricted. So all this, okay, so this is restricted to d omega. Obviously, this is also restricted to d omega. So one thing that seems to be crucial is the following, that so knowing lambda gamma, so the one intermediate step, so intermediate step is that let's say, for simplicity, let's assume that we have a C infinity conductivity. Okay, so then from the Dirichlet-to-Neumann map, so lambda gamma gives all the derivatives of gamma on the boundary. All the derivatives of gamma on the boundary. So, so the original result, sorry. So why is this important? Because you see that I need to, so in order to do this, okay, by the way, this is also restricted on d omega because there is this gamma to the minus half over here. So I need to know the knowledge of gamma on the boundary. And I also need to know d gamma, d nu on the boundary. So both information is required. Okay, so if you start with C infinity conductivities, then lambda gamma actually gives the derivatives of gamma on the boundary. So there are several approaches to this, but probably the simplest approach is based on the fact that the Dirichlet, so this lambda gamma is a pseudo differential operator of order 1, and so therefore, you know, the thing is. So you can actually, and then you consider the asymptotic expansion of the pseudo differential operator, or the symbol of the pseudo differential operator, and from that actually you can extract out all the derivatives of gamma on the boundary. So this is one approach, probably the simplest approach, and this approach is due to Sylvester and Ullmann. This was not part of their paper, the paper where they actually solved the Calderon problem, but this was one paper prior to that where they actually showed this. And but the original proof, so the first proof in this direction, so first proof is due to Kohn and Vogelius. And they use very clever elliptic estimates to actually show that you can actually determine. So the Dirichlet-to-Neumann map actually uniquely determines all the derivatives of gamma on the boundary, and so therefore, as a consequence of it, for real analytic conductivities, you can actually determine the conductivity based from the Dirichlet-to-Neumann map. So this was a paper. I don't remember the year, but it came in CPA. And this was also, I believe, the proof of Sylvester and Ullmann also is in a CPA paper. But this was the first proof is due to Kohn and Vogelius. Okay, so because you know from the Dirichlet-Neumann map, that is from this lambda gamma, you can actually determine all the derivatives. So okay, so for C2 you can actually determine d gamma d nu as well as this gamma at the boundary. So therefore, from the Dirichlet-Neumann map, you have the Dirichlet-Neumann map corresponding to the Schrodinger equation. Okay, so therefore it's enough to study. Okay, it's not quite enough, but it's so we will first focus on this problem. So it's enough to study the following problem, which is minus Laplace plus Q, U is equal to 0. U on the boundary is F, and then F going to du d nu, and Q is of a special form, which is delta, the Laplacian of root gamma by root gamma. Okay, and by the way, I'm assuming that gamma is in C2. All right. And so why is this important? So the reason why this is important is the following, is that suppose this Q were not to be present. Okay, so then the initial approach of Calderon asked us to look for solutions of the form e to the x dot zeta or I x dot zeta, where zeta is a complex vector. Okay, so the idea of Sylvester and Ullmann is to actually look for perturbations of the solution. So the idea, so this is a crucial idea of Sylvester Ullmann, to look for solutions of the form e to the x dot zeta times 1 plus r of x dot zeta, okay, where zeta dot zeta is equal to 0, which is not the dot product, by the way. And there is good control, and I will make this precise. And there is good control of R as mod zeta goes to infinity. Okay. So good in what sense? We will actually make this precise. So you see that this R here, so this is the perturbation, right? So if this R were not to be present, so if this R were not to be present, so then you actually have e to the x dot zeta, which is actually the solution to the harmonic, which is a harmonic function, because I'm assuming that zeta dot zeta is equal to 0, right? Now, so this following in the hyperbolic setting, such solutions were studied. These are what are called as real geometric optics. So following this, solutions of the form. So this is, let me call this as u of x zeta, where zeta is just a parameter. So solutions of the form u of x with respect to a parameter are called complex geometric optics solutions. Okay, right. Now you see that I just want to mention one important progress. So remember that in the first lecture we mentioned about this data on possibly very small subsets of the boundary, and again the solution, the approach of Koenig, Sjostrom, and Ullmann is again based on construction of complex geometric optics solutions. But so this is just a remark. So in Koenig, Sjostrom, and Ullmann paper, the linear weight x dot zeta is replaced by suitable nonlinear weight. So these are what are called as limiting Carleman weights. So it is modeled on the fact that you see that you have you still need that so in this case, right, you have zeta r plus I zeta I. So then the length of zeta r should be the same as the length of zeta I, and then these two should be perpendicular to each other. So these conditions should also be satisfied in the nonlinear setting. But the thing is that the zeta r corresponds to the the real part of the x gradient, and zeta I would correspond to the imaginary part of the x gradient of the weight. And so therefore the length of the real part, the gradient, the x gradient should be the same as the length of the imaginary x gradient, and these two should be perpendicular to each other. So this is what is called as the limiting Carleman weight, and this seems to be crucial. And they actually use very sophisticated analytic microlocal analysis combined with analytic microlocal analysis to settle the problem. So we are not going to do that. We are actually going to focus only on the linear weight, which is x dot zeta. And so now let us see how the proof proceeds. Okay, all right. So the idea here is that, so what I want to do is, the crucial goal seems to be that I want to find this R, okay, an R with suitable control at infinity. Okay, suitable control in the L2 sense. And this is what I want to do. And so before I do that, let us see why this is important. Okay, so this goes by the name of Alessandrini identity. So remember that when we considered the linearized Calderon problem, we ended up with an integral equation. So recall, in the linearized case, we had an integral identity. So what was the integral identity? The integral identity was integral over omega delta grad u square, or grad u dot grad v. This is equal to 0 for all uv harmonic. So the thing seems to be that you just need to produce enough u and v harmonic such that, you know, so this product, sorry, this dot product over here is dense in the L1 sense. Okay. Now the Alessandrini identity is the same thing. So you now what you have. So now the solution is the problem is the following. So now you have minus Laplace plus, let's say you have Q1 U1 is equal to 0, and let's say you have U1 restricted to d omega is equal to F, and you also have minus Laplace plus Q2 U2 is equal to 0, and let's say U2 restricted to d omega is equal to F. Now, so you have F going to du1 d nu and F going to du2 d nu, right? So, okay, I have, so this is du1 d nu and du2 d nu. These are in the formal sense, but if you want to really make sense of this, you can just multiply by v in this, and then do an integration by parts. Okay, so then the Dirichlet-to-Neumann map, right, would actually be grad u1 dot grad v plus q u1 v, where v is in h10. Okay, so that would be the definition. Okay, so so the Alessandrini identity is as follows. So now suppose so if nq1 equal to nq2, right? So nq1 corresponding to F going to du1 d nu. So this operator, and F going to du2 d nu, right? So if these two are the same, so then we have integral over omega q1 minus q2 of u1 u2 dx is equal to 0, where where u1 solves minus Laplace plus q1 u equal to 0, and then u1 restricted to d omega is equal to F, and u2 solves Okay, or in other words, what we have is so what we have is that u1 and u2. Okay, so if I don't put any assumptions on the any restrictions on the Dirichlet, right? So the condition that I have is the following, that so we want to look for solutions of the form e to the either ix dot zeta or x dot zeta times 1 plus r of x zeta. Okay, so now what we do is, so suppose we are able to construct such solutions. Okay, e to the x dot zeta times 1 plus r of x dot zeta. Okay, now let us just substitute this back into this particular equation, and let us also assume that we can have enough zeta 1 and zeta 2 such that when I consider the product over there, I'm able to get the Fourier transform. Okay, so we look for e to the x dot zeta 1 and e to the x dot zeta 2, right, such that e to the x dot zeta 1 plus zeta 2 is e to the I x dot c. Okay, so this product, So this product, so one coming from corresponding to U1 and the one corresponding to U2, okay, into this equation, So then what we have is, but you see that we also have this R over here, okay. So therefore, now what we will end up with, so now letting Q1 minus Q2 equal to Q. So then we will have Q of X, E, okay, maybe minus, E to the minus I X dot C, right? And then I will have 1 plus R1 times 1 plus R2 dx. This is equal to 0. This is equal to 0, right? But you see that this R1 and R2, they depend on zeta. Now, let's say in the L2 sense, so in the L2 sense, if R L2 goes to 0 as mod zeta goes to infinity, similarly Ri. Okay, so then what we have is that from this equation, I have shown that Q hat of C equal to 0. And that would imply that Q is equal to 0 almost. Right? Because you will have a term corresponding to R1 and also a term corresponding to R2 and the term corresponding to R1, R2, and then there is 1. But that 1 would give me Q hat and every other term is going to decay. Okay, so this control over here, this seems to be important. Okay, so so now what I want to do is the following. So now the next step, so the next step is to construct. So construction of complex, okay, I'll just write it as CGO solutions. Construction of CGO solutions. Okay. Now suppose I were to look for a solution to minus Laplace plus Q. I'll just put Q. Okay, U equal to 0, where U is equal to, let's say, E to the I X dot zeta or X dot zeta, doesn't matter, of 1 plus R. Okay, R also depends on X and zeta. Right? Now, suppose I were to substitute, so let's just substitute this back into this equation. So then what do I have? So what we have is that we'll have Laplace. Okay, so this is minus Laplace plus QU is equal to 0 if and only if E to the minus I X dot zeta of minus Laplace plus Q of E to the I X dot zeta of 1 plus R of X dot X zeta, this is equal to 0. Okay, so this implies that E to the minus I X dot zeta of Laplace of E to the I X dot zeta R, okay, so this comes with a minus sign, so therefore this is going to be equal to Q sorry, there is also Q. Yeah, minus, let me put minus Laplace plus Q of E to the I X dot zeta R, right? And that's equal to what remains, Q, correct? Right. So now you see that, now just pretend for a second. So now so if I want to show the existence of this R, obviously this R here depends on zeta, the zeta that you choose over here. Okay. So what we want to do is we want to show the existence of this R with good control at infinity in the L2 sense. Okay. Now the way we do this is motivated by this particular equation, right? We look at E to the minus I X dot zeta of minus Laplace plus Q of E to the I X dot zeta. Let's call this as R. This is equal to F, where this F is in L2. The right hand side F is in L2, where Q is in, actually Q is continuous because Q involves Laplace of square root. So therefore it's continuous on a bounded domain. So, okay, so you can, so now what we do is now extending it by 0 to outside of omega. So I have a function f which is in L2. Okay. Now what I want to do is I want to show the exit. So I want to first solve for this R and with good control at infinity. Now you see that this particular equation, this should remind of something which you might have seen in a different context. So the context being that this would have come up in unique continuation, right? So this is a conjugated equation. Okay, so the theorem is as follows. So let me just take the theorem. Right. So if you just expand this, so expanding this, actually it doesn't matter, but I just want to expand this. So we would get the following equation. Okay, so it's going to be, so let me put dj as 1 over I, where I is the complex, ddxj. So dj is this, and so the equation, so when I expand this out, right, so the equation that I would get, this is just a simple calculation, so I'll just leave this to you. So you have d square plus 2 zeta dot d plus qr equal to minus q. And as I told you, we are not going to consider this, you know, the same proof will actually work for any f as long as this f on the right hand side. So I'm not actually going to consider the q on the right hand side. I'm just going to consider any general f. Okay. So the theorem is as follows. So this is the Carleman estimate. The Carleman estimate. So there exists a constant C depending only on n and omega, such that for any zeta in Cn, okay, zeta dot zeta is equal to 0, and we can also take mod zeta, and f in L2, then the equation d square plus 2 zeta dot d plus qr equal to f has a solution r in H1. If you're not you know, for those of you who are not too familiar with sub-Borel spaces, it doesn't matter. Just think of this as some functions, but this is what is important. And r H1 of omega. So this is less than or equal to C naught by mod zeta. But so this is where, you know, I did not make this precise over here when I actually multiplied this R1 and R2, right? But you see that, let us just look at this estimate. Actually, I did not, I'm not writing this, but you can also, sorry, this is not RH1, this is RL2. In fact, you can also, because R is in H1, you can also get some estimate about this as well. So this is some, but this is not needed. Okay, so just look at this estimate over here, right? Now this, sorry, C naught. So the constant C naught over here, so this is independent. So now you see that the R in the L2 sense is going to be bounded by some constant which is independent of, you know, the parameters. And now you let this mod zeta go to infinity. So because of that particular reason is why you have that in this particular case, anything involving R1, R2 or R1, R2, that's going to decay. right? Those are not going to appear as part of the, those are not going to appear when you let mod zeta go to infinity. So therefore, you will actually end up recovering the, you will actually show that the Fourier transform of Q is 0. And that shows the uniqueness. Okay, now you may ask me that I have only shown uniqueness for Q, right? But the problem about uniqueness for gamma still needs to be solved, right? But that's not very hard. Okay, so I'll come back to that in just a second. But I want to emphasize as to how one actually gets this this Carleman estimate, right? So RL2 actually this particular thing is not part of. This is not part of this Carleman estimate. Actually, you need to work a little harder to get this estimate. Okay, so you only need this. So only need this. You only need this, right? Because that's the only term that's going to appear in this R1 and R2. So anything involving R1, anything involving R2, or the product, right? So you only need this. This can also be solved, but you need like an H1L2 Carleman estimate. Okay. But you see what this is saying. What this is saying is that so what is it that we have over here? If I just transform this equation, what do we have? What we have is that we have RL2 is less than or equal to some constant over mod zeta times e to the minus I x dot zeta of minus Laplace plus q of e to the I x dot zeta R L2. So this is what I mean by saying it's an L2 Carleman estimate, right? You can also get H1. So instead of this over here, you can also get an H1 L2 Carleman estimate. In fact, you can also do much better. You can also get an H2. So here, in this case, H2 and L2 Carleman estimate. So H2 Carleman estimate, you have to use the Garding's inequality. Okay, but for our purposes, you see, the reason why you also need this H2 L2 Carleman estimate is when you have lower order coefficients. In fact, if you have so instead of just the 0th order term, right? So maybe I'll just mention this. Let me just complete the thought process here, and then I will actually mention some of the extensions of these problems, right? Okay, so what is it that we have? So suppose we have derived this Carleman estimate, and I'm not going to give the proof of this. Now the proof of this is not very hard. It just uses Poincare inequality. Actually, the proof is easier because you actually have this x dot zeta, which is a linear weight, right? So when you actually consider the L2, right? And so first you start with, so first we derive a Carleman estimate without the Q term, and then we absorb the Q term. Then we absorb the lower order term. This is how it is typically done, right? Now, you see that the lower order term is a 0th order term over here, okay? But suppose you also have a first order term. So instead of minus Laplace plus Q, suppose you also have minus Laplace plus, let's say, W dot D, where W is a vector field, plus Q, something like this. Now you see that in order to absorb the W dot D, so first you derive a Carleman estimate involving just the Laplacian. And now what you want to do is you also want to derive the W dot D term. But in order to absorb the W dot D term into the Carleman estimate, L2 Carleman estimate, L2 is not sufficient. You need an H1 Carleman estimate. Okay, so that you can absorb the first order term. Okay, so that's the reason why H1L2 is required, and H2L2 is required if you are dealing with partial data problems, because then you have to consider the traces on the boundary. So for that you actually require higher regularity, of the remainder terms, and that's why you also require H2, because you will have not only R, but you will also have the gradient and things like that, which you have to restrict on the boundary, and for that you actually need H2 Carleman estimate. Right. For instance, suppose you are looking at a first order minus Laplace plus W dot D plus QU equal to 0, but with also a partial data. Right. So in order to a partial data, you also need to restrict the solutions on the boundary. But now you see that you also have a W dot D of the remainder. So, but you need the remainder. So the D of the remainder is now going to be one degree less. It's going to be 1 degree less smooth, but you also need to restrict on the boundary. So therefore, you actually require higher order estimates so that you actually can deal with partial data problems. So this is the reason why we actually work with H2L2 Carleman estimate. Okay, all right. So once we have derived this, so then as I told you, then the proof is actually quite straightforward, because now once you have derived this estimate, this estimate over here, then you go back and then you just substitute this back into R1 and R2. And once you have that, then you have shown that the Fourier transform of Q is equal to 0, and then you're done. Okay, so right. One thing that I wanted to mention is that then we absorb the lower order term. Now, one advantage, I'll just mention this, but I will not give the proof, is that so if you want to derive an estimate of this form, okay, minus or plus doesn't matter, e to the I x dot zeta r L2, right? Now, one advantage here is that okay, so this is a linear term, and this is constant coefficient. So when you actually consider the L2 inner product of this conjugated Laplacian, many terms vanish, especially the commutator terms vanish. And so what you will end up with is one term for which you can apply the Poincare inequality, and then that will give the answer. Okay, so let me not do this, but what I want to do is now I want to focus on so therefore combined with the Carleman estimate, we have actually solved the equation using the Alessandrini identity. But I still haven't explained one fact. The one fact being, where exactly have I used the fact that n is bigger than or equal to 3? Okay, so n is bigger than or equal to 3 is actually used to show to actually get to the Fourier transform being equal to 0. Okay, so n is equal to 3, n bigger than or equal to 3 is used in the following step. Okay, so what is that step? So let me actually give you the just 1 second. Yes. So now what we do is this. So now using the Carleman estimate. So using the Carleman estimate, we can get solutions of the form, okay, U1, which is e to the I x dot zeta times, okay, so I didn't mention this, but you can also get something of the following form plus R1, let's say, and U2 is e to the minus I x dot zeta times 1 plus R2. So you can also absorb this e to the I x dot c into this, it doesn't matter. Okay, so then you will have R with e to the minus I x dot c, but RL2 or R with R multiplied by e to the I x dot c L2, they have the same L2. So the L2 norm doesn't change. Okay, and what are my C? So C is a fixed. So C is a fixed vector. In Rn. So that's one thing. And zeta is a complex vector of the form. Okay, so zeta is equal to omega 1 plus I omega 2 by h, where omega 1 and omega 2 are okay. So the length of omega 1 should be the same as length of omega 2, but I'm also interested in mod zeta going to infinity. So I can have h to be a small, this h here to be a small parameter, and then as h goes to 0, mod zeta will go to infinity. Right? It's just a minor rearrangement. That's it. So omega 1 and omega 2 are unit vectors, but you see that in order for zeta to be a complex geometry, for zeta to be a solution corresponding to the okay, in order for e to the I x dot zeta to be the solution to the Laplace equation, you actually needed that zeta dot zeta is equal to 0, which would mean that the length of the real part of zeta is the same as the length of the imaginary part. That is established because I have omega 1 and omega 2 being unit vectors, and then I have divided by the same h. So that's established. But now I also need that omega 1 and omega 2 are perpendicular to each other. Okay, so we also need omega 1 and omega 2 to be perpendicular to each other. Okay, that still doesn't quite explain why 2 dimensions. So right now it will work with 2 dimensions, right? So there is nothing that that prevents us, but there is one more thing over here. So remember that I put this e to the I x dot z x dot c over here. Now as I told you, you can absorb this e to the I x dot c back into this e to the I x dot zeta. Okay, so then it would mean that I need to construct 3 vectors which are mutually perpendicular to each other. Okay, but if I just put this e to the I x dot c as part of this particular equation, then I need to have one more condition for this to be a solution, because this is obtained by just substituting this back into the equation. So the condition that I would require is the following. So let me put this as star. So in order for star to be a solution, we need zeta dot gradient of e to the I x dot c to be equal. So for those who are familiar with it, this would be the first term in the transport equation, right? So the transport equation also has to be solved. Therefore, then what you will do is, so once you set the transport equation to be equal to 0, then you will have something only involving the remainder, and that remainder term is what we get from the Carleman estimate. Okay, so in order to, so now you see you have zeta dot grad of e to the I x dot c to be equal to 0, but this would mean that zeta dot c to be equal to 0, and this would mean that omega 1 dot c is equal to 0 and omega 2 dot c is equal to 0. So you start with the initial vector c. Now you must have so now you consider the perpendicular plane. Now in the perpendicular plane, you need to produce at least 2 mutually orthogonal vectors, so that these 3 form a mutually orthogonal system. So now you see that you can only do this in 3 dimensions and higher. So that this is the place where 3 dimensions and higher crucially plays a role. Okay, so once you have this, now when you substitute all these things back, you see that because I have this e to the I x dot c and e to the minus I x dot c, and you have this e to the I x dot c over here, right? So when I multiply anything involving R1 as h goes to 0, that goes to 0 because of the Carleman estimate. Anything involving R2 also goes to 0 by the Carleman estimate. Anything involving R1, R2 also goes to 0 by the Carleman estimate. Okay, so therefore what you will end up with, you will recover the Fourier transform of Q, or you will show that the Fourier transform of Q is equal to 0, and therefore the proof is done. Okay, so hence, so here is where, okay, here is where n bigger than or equal to 3 is used. So hence the Calderon problem for the Schrodinger equation is done. But we still haven't solved the conductivity equation, because our goal is to actually solve the conductivity equation. Okay, so but this is actually quite simple, right? Why? Because now we have shown, that Q1, which is Laplace root gamma 1 by root gamma 1, right, is equal to Q2, which is Laplace root gamma 2 by root gamma 2. Okay, so now recall, I actually mentioned this. So from Cohn-Vogelius or by Sylvester and Ullmann, that n gamma uniquely determines gamma at the boundary. Okay, so therefore what we have, so because n gamma 1 is equal to n gamma 2, right? So we have shown n gamma 1 equal to n gamma 2 implies Q1 is equal to Q2. We also have gamma 1 restricted to d omega equal to gamma 2 restricted to d omega. So we have these two, this fact as well. Okay, so now because Q1 and Q2 are of this special form, right? So what does this do? This motivates us to look for the following equation. Minus Laplace plus QU is equal to 0. Okay, now note that, so look at, now note that, let's see, root gamma 1 and root gamma 2 are solutions to this equation, right? Because that's exactly what I have, right? Because I have, so suppose I substitute u is equal to root gamma 1, so I get Laplace root gamma 1 plus q. Okay, so q, okay, sorry, where q is q1, which is the same as q2, right? So whether I consider gamma 1 or gamma 2, I see that it actually satisfies this particular equation. But we also have that root gamma 1 and root gamma 2 are same on the boundary. So therefore, by uniqueness, so hence by uniqueness, we have because remember that I mentioned that for potentials arising out of the form Laplace root gamma 1 by root gamma 1, it's actually a well-posed problem. So therefore, the solutions are going to be unique given the boundary data. But you have two different boundary data which are the same. So therefore, the solutions have to be the same inside. So hence, hence in dimensions n bigger than or equal to 3, Calderon problem with C2 conductivities and full Dirichlet, full data. Yes. That completes the proof. Okay, so now there are many problems that one can ask. So I have 1 minute. So let me actually mention one interesting problem. So current work. So for instance, you can look at, okay, so you can look at D plus W square plus Q U equal to 0. So instead of looking at just the so the leading order term here is still going to be the Laplacian, Remember, d is 1 by I d by dxj, right? But you see that there is also a first order term, right? The first order term being this w here, which is a vector field. Now, unlike the Calderon problem, so here you cannot determine all of w. In fact, there is a gauge invariance, so you can only recover a component of w from the boundary data, the Dirichlet-to-Neumann data. You can only recover the curl of w. You can recover all of q, but you can only recover the curl of w. And one can similarly ask for partial data versions of these problems, and one can also ask for partial data in the same part of the boundary. So there are several variations of this problem. So it is still an area of current active research. There are many interesting problems which are still open. Before I end, so some references. So as far as an introductory reading is concerned, I would definitely suggest Mikko Salo's notes. Then the paper by Sylvester Ullman. Buchheim Ullman. And Koenig Sjöstrand Ullman. So I will stop here. Thank you. Any questions?
Sir, I have one question.
Yes, please.
So what was the idea of convegulius to proving gamma 1 equals to gamma 2 on the boundary?
So they actually produce highly, okay, I don't, it's been a while since I read that paper, but as far as my memory serves, they produce oscillatory solutions concentrated near the point where they want to construct, they want to show that gamma 1 is equal to gamma 2. So this is just a rough idea. I don't, it's been a while since as I told you that I saw the paper, because there is now this modern approach using pseudo differential operator technique. But if you go back to Kohn and Vogelius, what they do is they produce highly oscillating solutions which are concentrated near the point where they want to show that gamma 1 is equal to gamma 2. That's the roughly the idea.
Thank you, sir.
Yeah.
Hello, Venki.
Yeah, tell me.
Yes, thank you for very nice talk. I just want to ask that, is there a survey paper where one can look like what have been already done or what are like current open problems? Some review article kind of thing related to these topics?
See, I don't know if Gunther has written something recently. Yeah, I see. You mean like what are still the open problems in the area?
Yeah, like if somebody is new and want to know like how much has been done and what are the current research problems in this area.
Yeah, I don't know if there is any recent survey article. I have to check. But probably Gunther has written something in, there is this Chinese, I remember an article in a Chinese journal. It's like some Chinese series A or something like that, where there were some survey articles. So I have to look it up, but I'm not exactly sure.
Okay.
Any other questions? Okay. All right. Thank you very much. And Hope to see you all at 6 o'clock for two hints talk. Thanks. I'll stop sharing now, and I'll post these lectures on the resources webpage. Okay, bye-bye.